Good morning, everyone. Thank you for joining in for this joint webinar between Kratos Analytical and Spectral. I think we can see people are signing up quickly now, just as at the hour, but I think we will still get going to. We have a busy schedule ahead of us, Adam, don't we?
We do. It's exciting to see so many people joining us. So I'll just introduce myself as well. I'm Adam Roberts, job title Marketing Manager. I've worked for over 30 years now on using XPS and surface analysis. Job title Marketing Manager at Kratos Analytical. So we manufacture, sell and support X-ray photoelectron spectrometers. And we've been working with MATS for, I think, 25 years.
It's an anniversary.
Yes, silver anniversary.
Yeah, sorry, I didn't bring the cake today. I should have brought a nice cake to celebrate. Yeah, I'm trying to match your 30+ years, but I noticed maybe, to be honest, maybe 30 years for me is about correct for my experience in SEM work. My name is Mats Eriksson, and I run a company called Spectral, which is the Nordic extension of Kratos Analytical. We support the Nordic countries in Europe. No, great, and thanks, Adam, for joining in and doing this together. I think it's an interesting topic that we'll try to dive into today, to look at just, it's all, I find that always that you kind of stick to your techniques that you're using, and it's always good to see, where are the benefits and the sort of the drawbacks or disadvantages of different techniques. And luckily for us, there's no silver bullet with just one technique that solves all the problems. That's, in a way, that's the essential starting point for Spectral, isn't that we would be out of business if one instrument would do it all.
Yes.
But I think that there are interesting things to do. Yeah, so maybe just a comment for those of you that don't know Spectral, as we are organizing this series of webinars. Spectral is a Nordic distributor, so we're really a sales and support organization working in the field of electron microscopy and surface analysis. And as Adam mentioned, we've worked together with Kratos for 25 years. I think 2001, I think, was when we kicked off together. But also a lot of stuff that are related to these core, big instrument technologies, that we look for ways of enhancing what you could do with them. So adding in situ experimental tools, adding software in post-processing or automation, or of course also sample preparation is interesting, and there's many times also a limiting factor to what you can see. That's what we do, and doing that, we have collected a bunch of partners, and for some of them we are the exclusive channel into the Nordic market, and for some of them we are simply working really closely together to try to solve customer problems and to bring benefits to all of you guys that are joining the webinar today. Yes. So, and just before we kick off with this one, just a reminder that on the spectral.se website, we also have recorded webinars. So the ones that we've been doing, we record, and again, you could look at them at your leisure when you have time, or if you want to share stuff with colleagues, of course. I think also maybe that's a little practical thing for today, that we will record the webinar and it will be available. It maybe takes us a week or so until it's published, but then you will be able to have a look at it when you have time. We also like the webinar to be very interactive, so you have the options of adding questions in the Q&A section, and sometimes when those questions fit into the discussion we are doing, I'll bring them in and interrupt either myself or Adam in what we're talking about to enhance what we say, or we also have a Q&A. We'll try to answer as many as possible of the questions that you post. Otherwise, we'll follow up with email to do that. Anything else, Adam, that I should mention?
No, I don't think so. I think we're good to get started.
I think we'll try to be like within an hour, I think, with including the Q&A, but let's see how we do with that. Sometimes I get carried away and it just takes a long time to do things.
Yeah.
But anyway,
okay,
let's go ahead.
so I was just going to sort of start by putting XPS in a bit of context for surface analysis and more generally materials characterization. So often we want to determine the sort of surface, the bulk, the mechanical and the electrical properties of a material for a particular application. And as Matt's rightly said, no one analytical technique is really going to give us all those answers. So we appreciate that XPS, X-ray photoelectron spectroscopy, is part of the toolkit that the modern materials characterization scientists can use for their work. And we think that there is quite a bit of sort of synergy between SEM, EDX and XPS. And over the course of the next sort of half an hour, 35 minutes, we'll try and highlight both the strengths, but also the considerations of where one technique might excel over the other. So I think we were going to start first of all with a poll, weren't we, Matt? So we were going to just see, get people to answer which materials characterization techniques do you use?
Yes, I think I like the polls because it gives us maybe a flavor of the audience, what they are interested in, and their main challenges and their background. Of course, we'll try to address accordingly to the stuff that we see. So I'll give you a few seconds just to give me some answers. It's also a good test to see the audience, how awake they are. I mean, it is depending on where you are on the globe, right? I mean, it's 10 o'clock in my time zone, it's 9 o'clock in the UK. But actually, the webinar today is quite global. I think we have participants from many different countries around the globe. So anyway, it's a test, but it's good. It looks like 2/3 of the audience is awake. That's good. I like that.
Do you publish the result? How does this work?
Yeah, I will just I'll give just a cliffhanger still, and then maybe I will publish. So 70% of people have answered. So we can see that actually 85% are using SEM and EDS, and 66% are using XPS. Those are the two sort of largest, but also many use, of course, optical spectroscopy or optical microscopy, Raman, FTIR, AFM. So there's a nice mixture with almost the same amount of people using both, coming from an SEM EDS background and from an XPS background. So I think that really what I was hoping for, that we can really address both sides of that story, I think.
Yes.
Sounds good. Yeah, great. Super. Let's continue.
Okay. So I think you were going to kick off with just an overview of a sort of introduction for perhaps our XPS colleagues who are less familiar perhaps with the sort of processes behind SEM and EDX.
Yeah, I think it is important just to go back to those very much fundamentals, right? I mean, we talk about XPS or surface analysis. What is, what do you mean surface? What is, how close are we then to the actual, atomic surface that we see? And SEM, or in the XPS community, SEM is seen as very much a bulk technique, and I think as in the SEM community, it's kind of depending on the settings and the detection principles that you use. But of course, we are bombarding with electrons, and we are creating inelastically scattered secondary electrons from the outer electron shells of the atom. And those have low energy. So we can see there's an energy diagram on the top right, where you see there are secondary electrons almost per definition below 50 electron volts. And then there are backscatter electrons that are fully or partially elastically scattered, so just bouncing in the material and back again. And as the secondary electrons have low energy, they really come from the top, maybe 10 nanometers from the surface, with the energy that they have. But the electrons, especially at a high primary electron energy, they can escape from rather deep in the material. So just a reminder of that. So next slide, please. Yes. And if we look at that just practically from this compound sample where we have a nickel particles in an alumina matrix, and it's imaged with 1 kV primary electrons and 10 kV, and you can see that actually the interaction volume, so basically the scattering distribution simulated with a Monte Carlo simulation, just see how large the difference is. So if you want to do surface imaging, as you can see, the 1 kV setting gives me much more surface related information versus the 10 kV. I think we all know that, but in a way, when you, again, always when I think about it and you see that the relationship between penetration depth and primary electron energy is almost proportional to the square of the energy of the primary electron. So it has really a large influence, and we'll look at some examples of that going forward. Thanks. Next slide, please. So also interesting to look at. I mean, now we're in the SEM, we're bombarding with electrons, and we look at photons coming out, and in a way, XPS is the opposite, right? You bombard with photons, and then you look at X-rays coming out. We're talking about the different electron shells or energy levels in the atom, and we use different naming flavors for that, right? So you talk about the energy levels, 1s, 2s, 2p, and in the EDS world we talk about K alpha or K beta or L alpha radiation coming from the transitions between those energy shells.
That's
so
right.
Just important sometimes to keep that in mind.
Yeah. So I was then going to just give again a very sort of basic overview of XPS. So as Matt's indicated, we have this is just the electronic structure of aluminium, and again the sort of different nomenclatures that we use in a sort of XPS world. We're thinking in the spectroscopic notation, but they're equivalent to the sort of X-ray notation for those different quantized orbitals. So for XPS, we have a monoenergetic X-ray beam. Classically, that's using aluminium K alpha, and that X-ray photon has enough energy to excite a photoelectron from either a core level, a particular core level, or the loosely bound valence electrons. And it's this photoelectron which we're measuring. So we typically measure the kinetic energy. So that's what we're measuring in XPS. And that's related to the binding energy of that electron in the orbital by this very simple equation. So we know the photon energy, so that's the energy of our X-rays. We're measuring the kinetic energy, and then we have another term, the work function, which is fixed and is typically used as the work function of the spectrometer. So that allows us to calculate this binding energy. So going forward, we'll be talking about the surface sensitivity and the relationship between the kinetic energy and the binding energy. So let's have a look where the surface sensitivity of XPS derives from. Essentially, we have the relationship between this kinetic energy. So if we plot the electron kinetic energy, so the energy of the electrons that we are measuring versus the inelastic mean free path length, we can see we get this so-called universal curve. So the elastic mean free path is the distance, the average distance between two scattering events. So in effect, it's the distance that those photoelectrons can travel through the material before they're scattered and they don't emerge from the surface and are measured by the spectrometer. So what does a typical XPS spectrum look like? Again, you're probably very familiar. This is a survey spectrum, again, from just a regular piece of domestic aluminium foil. So you can see that we have these peaks sitting on a rising background. And we can scan over the entire energy range that can be excited by my X-rays. We can also identify from those peaks, their peak positions, the core levels which they were ejected from. So very quickly we can get sort of a fingerprint of the elements within the volume that I'm measuring. And we can think either in binding energy or the inverse kinetic energy. So in my spectrum, this end, the low binding energy, high kinetic energy, so that will have a greater sampling depth. This end of my spectrum is more surface sensitive, so higher binding energy, but lower kinetic energy. More surface sensitive, can't travel as far through the material. So in the technique, XPS, this survey scan may be enough to answer the question that we were trying to determine. In this case, we're seeing just a little bit of fluorine. That could be contamination of the surface that may prevent adhesion. So just a very simple elemental information from my material may give me the answer I'm looking for. But the real super strength of XPS is its ability to determine the chemical information in the top 10 nanometers of the surface. So if I go in and do a higher energy resolution scan around my aluminium 2P, we can see that we get an aluminium 2P spectrum with chemical information. So I'm seeing aluminium in an aluminium environment, and I'm also seeing aluminium in a sort of oxide environment. So we're getting that chemical state information, and that really is one of the great strengths of XPS, that you're getting that chemical information from the top 10 nanometers of your surface. So XPS is surface sensitive. It's going to give us elemental information. We can determine chemical state, and it's also quantitative. The area under the peak is directly proportional to the amount of those elements present in the surface volume we're detecting.
I think it's nice there, Adam, that actually, you know, you had the terminology XP or ESCA as well.
Ah, yes.
Right, and I think this, in a way, is a good cue for you know, the connection to Uppsala and Kai Siegban, who got the Nobel Prize for initially developing the technique, right?
Yes, electron spectroscopy for chemical analysis, ESCA,
Yes.
which has largely fallen out of favor as the sort of acronym. So let's think about why XPS and SEM EDX are complementary. Well, if we think of the information we're getting from XPS, we can begin to ask questions: is the element truly part of the surface, or are we seeing a subsurface artifact? So XPS can shed light on EDS type measurements, mapping measurements. There's also the question of the chemistry, which we've talked about. So if we think again now about, previously our aluminium foil was laterally homogeneous, but heterogeneous on the depth scale. And now in my model sample, I've buried a gallium nitride structure, but that's, let's say, for the sake of arguments, it's at 50 nanometers. So it's beyond the sampling depth of XPS. So if I look at now the image of the surface, so we look down on this surface, my EDS image would probably quite clearly show this gallium nitride buried structure. But my XPS image, where the information is only coming from the top 10 nanometers, would show a uniform homogeneous surface. So we would get two very different images depending on which technique we were using, because of that sampling depth difference. Just also another sort of advantage of combining the two techniques would be explaining perhaps ambiguous results that you might get without morphological context that XPS could give. So if we think of now our same sample, aluminium oxide on aluminium metal, but the sample is now very topographic, what can happen because we have a sort of fairly focused X-ray beam? This topography can cause shadowing of the X-rays. So I've got an area of my sample here where the X-rays are not hitting the sample. I'm not creating photoelectrons. So all of a sudden, my XPS image has this dark band where I'm not generating photoelectrons. And I may think that I've got distribution of the aluminium at the surface, but it's just purely a topographical effect. So that's where the two techniques can be very complementary to each other.
I think also that example with the shadowing, I think in most SEM EDS systems, you would have the same issue, because normally also the EDS detector would sit in an inclined angle and looking down at the sample, and you would see the structure or you would probably see the structure in the SEM image, but in your mapping result or so in EDS, you would probably have the same shadowing issue that you need to think about again and not to misinterpret.
Yeah. So whilst we're sort of still on our aluminium sample, again, this is my survey spectrum, which we've seen already. What I'm going to think about now is the depth distribution, and by changing the energy of my photons, so by using higher energy silver L-alpha X-rays, I can actually begin to look deeper into my material with XPS. So if you remember, we said the photon energy of the aluminium is around about 1500 volts. If I increase that energy, it means that I can excite photoelectrons with greater kinetic energy. So these guys up this end have much greater kinetic energy. So if we look at that ratio of the metal, so we're looking deeper into the material, I'm seeing more of the metallic aluminium relative to the oxide at this end of my XPS spectrum, relative to the aluminium 1s, which I can now excite with the higher energy. I kind of ran out of, with the aluminium, I run out of photon energy. Changing to the higher energy HAXPES source, I can begin to excite the aluminium 1s. And relative, this is more surface sensitive. So we're seeing relatively more of the oxide to the metal. And that's directly a consequence of this difference in kinetic energy, and therefore the sampling depth of my photoelectrons. So that's a really nice example where we can get depth information just from a single survey spectrum. So there's a little sort of schematic of where the two relative depths of information are coming from. So that's looking over a sort of a passivation layer on aluminium foil. So let's look at some actual data. So if we look, what we measured here was some alumina that was grown with different film thicknesses. So a series of samples with different alumina overlayers on silicon, and we measured or plotted the relative thickness of those layers against the actual measurement of ellipsometry. And you can see I could measure up to about sort of 7 nanometers with my aluminium excited X-rays, but I can look deeper with the silver X-rays. So that's really nice that I can get that depth information. And with XPS, we can do an angle resolved experiment. So the extension of this was to measure film thicknesses of unknown thickness, where we'd got an alumina barrier layer and a hafnium oxide overlayer. And by doing this angle resolved experiment, we were able to then use some software that we've developed to calculate a non-destructive depth profile. So we're looking at the atomic concentration versus depth. And that allowed us to determine the film thickness of 2.5 nanometers of the alumina barrier layer. And what was really interesting was that we were also able to identify some carbon contamination sitting between the alumina and the silicon. And that was up to a depth of nearly 15 nanometers because I was using the HackSpes. So have you got some, I think you've got a couple of slides, Matt, on surface sensitivity of SEM.
Yeah, I think it is. I mean, again, the focus on surfaces. I think that from one point of view, you could think about why the big interest in that absolute surface that we are talking about, or the top few nanometers. But I think there are so many properties that are defined by the surface chemistry and the surface layers. I mean, all around chemical reactivity, adhesion, and there are so many things that practical aspects that are defined by the surface chemistry. So looking at, so this is a lithium-ion battery electrode surface where, and again, I'm trying to push the SEM EDS envelope a little bit here. These are imaged at 200 volt landing voltage. So that's a very unusually low energy for the primary electrons, which means that my interaction depth or the penetration into material is very much coming very close to XPS surface sensitivity. But also here, what this illustrates is that if I then can add an energy selective electron detector in the SEM, which actually many of the advanced SEMs start to have, and you can see that on the energy scale with the secondary electron peaks on the left side and the backscatter sharp peak on the right side. The red area that I've illustrated there is to show that on the left-hand image, I'm only collecting low energy secondary electrons. So again, they can only escape from the very top surface. Compared to the right-hand image, again, only 200 volt landing voltage, but still here I collect basically all the electrons that are emitted, both secondaries and backscattered, even though those definitions start to blur a little bit when you are at these very low voltages. But then you can see that, again, the image on the left shows there's variation on the top surface. In the SM, I don't know what that is. That's hard to say. I don't have any chemical, I can see a contrast, but I don't know why is that contrast there. Is that because of atomic number? But it could also be, like it's mentioned in the text there, it could also be because of variation in surface potential. So the surface chemistry could cause a variation in chemical or in electrical conductivity, which then results in a contrast change. So it's just interesting to see that this imaging capacity then matches XPS sensitivity. Of course, again, with high lateral resolution and at the same time. So then we tried on this sample here to analyze that area. At 200 volts, I don't get any X-rays emitted, basically. So we need to increase the primary electron energy a bit. So even here, 2 kV, unusually low for EDS measurement, but still actually at 2 kV, you still get a bunch of peaks. But as long as the chemistry is not too complex, you could separate and you can get some reasonable results out of. And here we can see that, again, the 2 kV image in the center, we don't see contrast anymore from the different grains. But in the maps, we can start to see there is a certain variation in specifically fluorine distribution on that surface. So just a nice example to see that, again, how we could match what is done in the SEM. So on the other part of the spectrum of electrons in the SEM, when you look at the backscatter electrons, so if we say that okay, the backscatter generation is like a sometimes a long series of collisions in the material that finally lets a backscatter electron escape. But if you have a lot of collisions, you will also have some energy losses. So if we then limit the backscatter collection window to only electrons that are truly elastically scattered, so that have not really bounced around in the material and lost energy, that will also, the probability of them coming from the very top surface is really high then. And here we can see again, same energy, 1 keV primary electron energy. And the bottom image is a traditional backscatter collection image with Z contrast. But then on the top image, the energy filter has been added to remove any backscatter electrons that have lost some energy in the collisions. So again, from the surface, and we can see there is surface contamination there. Again, nice lateral resolution. Of course, we don't know what it is, right? I mean, especially in the SEM, probably this is an organic contaminant on that surface. We can see it's dark, so I think it's probably, mainly hydrocarbons. But what it is hard, and I think that brings us over to the next sort of really nice capability of the XPS. If something like this is seen, you can't see that distribution, right? But maybe you can find out what is it.
That's right. And then also a sort of supplementary comment to that I was going to make, related to, I think, as you just briefly mentioned, the fact that we've got photoelectrons leaving our surface for XPS. If we're trying to analyze polymer materials or non-conducting materials, very quickly, because we've got electrons leaving, the surface can become positively charged. So what we need to do is to use some source of charge neutralization to control the potential at that surface, because obviously any positive charge will change the kinetic energy of the photoelectrons which I'm measuring, and that's what's giving me this sort of chemical information. And what this slide shows is that we're able to identify these small shifts or chemical shifts in energy of the core levels to give us the chemical information. So this is a standard that we quite commonly use in XPS to look at the charge neutralization capabilities, PET. But the answer isn't always obvious, because we may have different materials where the chemical environment of the elements is identical, and this would be the case for polypropylene and polyethylene. So if I look at the carbon 1s spectrum for these polymers, there would be no way to distinguish between the two. So I've got now quite a nice example of quite a complicated, very common material, but actually really quite complicated. So the sort of laminated multi-layer material used for packaging potato chips or crisps. So if we do a large area survey spectrum of an area of my potato chip packaging that has been opened, so we've created a seal and then we've opened the packet, and there's been failure so that we can get to the crisps. If I do a survey spectrum from an area of that seal, we can see that we're seeing both aluminium, carbon, and oxygen in the spectrum. And that aluminium is used as a barrier layer to stop oxygen permutation into the packet, and keep the nitrogen in there that keeps the crisps nice and crunchy. So I'm seeing some aluminium in my spectrum. So we've talked about sort of homogeneously uniform samples analyzed by XPS. This is in fact an inhomogeneous laterally, and by acquiring a series of XPS images over a stage movement, we can look at the aluminium distribution, and we can see that it isn't indeed homogeneous. There are sort of islands of aluminium surrounded by carbon in this case. So now I'm looking at a sort of 400 micron field of view. I've imaged the aluminium, the carbon, and the oxygen. We can see that there's a correlation between the aluminium and the oxygen, and where we have high signal, we have low signal in the carbon. So let's use the XPS to look in a bit more detail, so we can use selected area spectroscopy where we acquire data from only a 27, in this case, a 27 micron area from the two different areas that we've identified. And we can see that from the aluminium rich area, I am indeed seeing aluminium and oxygen, also quite a bit of carbon. But then from this area too, I'm seeing only the carbon. So we're getting quantitative, laterally resolved XPS images. But I still haven't fully characterized that material. So we can use the fact that we can determine not only the elements present, but also the chemistry present by looking in greater energy resolution in the spectroscopy. And again, we see our aluminium and aluminium oxide. We can work out by taking the ratio of those two components, we can work out a thickness of the passivation layer. So indeed, we've got a sort of a non-homogeneous area with sort of holes looking through to this alumina area. If I then take a spectrum from the sort of polymer region, I get exclusively carbon peak. That's the only peak that I'm seeing. The only other area that may give me an insight into the material is the valence band. And by acquiring the valence band and then comparing it to reference spectra from different materials, I can quite easily say that my polymer material is polyethylene, high density polyethylene, by matching empirically the two valence bands. So another applications example is that I've got here is exfoliated graphene on silicon. So as we know, graphene is very, very thin. So this is a low resolution optical image. We've got these graphene flakes sitting on a silicon substrate. The higher magnification optical image allowed me to identify a sort of region of interest. And then if we think of how XPS is working, if I image the silicon substrate, where I see the high signal means that we're not attenuating that silicon. So we can say that there's very little, if no graphene in this area. And then we can almost see, corresponding to the optical image, that the signal of the silicon substrate is attenuated as the thickness or the number of layers of that graphene increases. That corresponds also to the signal from the carbon increasing in brightness. So I've got a really nice correlation between substrate and the graphene layer. We can then, as we did with the CRISP packet, go and measure from selected areas, and we can use the ratio of the silicon substrate to the carbon signal to give me an idea of the different graphene thicknesses. So this sort of shadow layer here, we determined corresponded to about, 4 graphene layers. And we obviously still saw a little bit of carbon, which we see from any sample that's been exposed to native atmosphere before being introduced into the spectrometer on the silicon substrate. So I think,
again, comparing this with graphene so in this case here, I have some older images of graphene on a copper surface. So we can also here again, both images are acquired with the same primary electron energy, and the difference is that I have in the right-hand image limited the collection only to low energy secondary electrons. So again, if we say secondary electrons are up to 50 electron volts, maybe in this case we are concentrating on just a few electron volts of those secondaries. So again, they are very much surface related, and we can see it's difficult for me in this case to try to estimate the number of layers or so, what happens on the surface, but we can see a very different contrast compared to the left-hand image, which would be sort of the normal secondary electron image in SEM, where you almost, well, when you know they're there now, right, we can very easily see them, but beforehand it almost looks homogeneous from a graphene, what should we say, coverage point of view.
Yeah. And then, you know, again, sort of thinking of this demonstrates here the different sampling depths. So for conventional XPS, sort of 10 nanometers. For the harder X-rays, in this case, this plot was for chromium X-rays, where we're looking even deeper. So we're looking up to about sort of 20 nanometers in that case. If we contrast that to EDS calculations using a 15 kilovolt primary electron, you can see that we're sort of sampling microns. So where we've got the very, very thin sort of graphene layers, XPS is really a sort of go-to tool. And as we've highlighted previously, we're then able to really determine the chemistry, and there's some nice little sort of tricks. So these are our reference spectra for a graphene material, and it has this sort of a very characteristic asymmetric carbon 1s spectrum. But then we can also start to look at does my spectrum look like if I've got maybe organic compound on top or contamination. And you can see that we get sort of still we see the substrate, the graphene substrate, but this organic material on top, which is much more in a sort of sp3 type bonding geometry. And a nice little tool which the XPS community will probably be quite familiar with is to actually look at the carbon Auger. And if we take the first differential, we can measure this so-called D parameter, which is the difference between the kinetic energy of the maximum and the minimum. And this can really give me a really good handle on the amount of sp2 and sp3 type carbon bonding in my material. And this is some work published by Dave Morgan et al., where we go right from the sort of sp3 of diamond to the sp2 of HOPG, highly orientated pyrolytic graphite. And you can see that plotting the sort of, or measuring the D parameter for these different materials really allows us to identify unambiguously the amount of hybridization and sort of sp2 type character. But it does come with the caveat that there are other features in the spectrum with similar sort of kinetic energy that could compromise those measurements. So whilst I would advocate looking at that D parameter, depending on the materials that you're measuring, you have to be careful of that interpretation as well. So I think the next thing is a poll, again, that sort of wake up question.
Yes.
We have
yeah, just interesting to see. I mean, now we've talked about those the different techniques, and actually, when we're doing this, we got some what you would say constructive feedback that we missed to comment on glow discharge optical emission spectroscopy as another technique. And of course, there are there are a bunch of other techniques as well that we could use for surface, or maybe not, but yeah, surface characterization, and of course also depth profiling. That's a very industrial tool, I think. So if we look at now, so I can see the engagement is a little bit lower than last time. So there has been some snoring in the background in some office. Okay, the percentage goes up now. Yeah, that's good. That's good. Yes, I like that. So what are the most common answer would be detecting trace elements, but very tightly followed by identifying contamination, understanding chemical states, and then a little bit less on analyzing organics or linking chemical information to what should we say, lateral distribution or the SEM images. Well, that's great. Thank you.
So I think our sort of final example, we're sort of coming towards the end now. So now we're going to really sort of push the capabilities of, I think, both XPS and SEM. And we're going to just spend sort of maybe 5 minutes looking at nanoparticle materials. Conventionally, XPS is beginning to get out of its comfort zone. There are challenges of analyzing nanomaterials with XPS. Obviously, if we think about the sampling depth of the technique, it's very comparable to the actual size of the nanoparticles. You can get problems perhaps with charging. Non-uniform differential charging can be a problem. Just sample preparation. So nanoparticles tend to agglomerate. There was a VAMAS study by the National Physical Laboratory looking at sample preparation prior to surface analysis, which did give some very interesting results and demonstrate just how variable and how important sample preparation can be. And then there's the sort of challenges of X-ray beam damage and quantification. But I'll just by example show you where XPS can be useful in analyzing nanomaterials.
I mean, this you would spontaneously believe this is a very challenging area, because again, we XPS has a very limited spatial resolution. So you're so far away from looking at 10 nanometer particles
Right.
in your lateral imaging capacity, but still,
that's right.
It's an interesting example, I think.
Yeah, there must be the obvious sort of assumption that we are averaging over an area that will hopefully be representative of the nanoparticles. So this is just an example of some copper nanoparticles on HOPG, and very quickly, rather than just acquiring a single survey spectrum from an area that we would then say was representative of the material, what we can do is use this array analysis. So I did a 10 by 9 survey spectrum set, and that gives me 90 survey spectra over this sort of 12 millimeter sample. And if we plot that in a color scale, we can see that perhaps not unexpectedly, the copper nanoparticles were not uniformly distributed over that sort of macro area. And that's quite important. So it allowed me to identify a particular region, a particular area of interest to go and look at with my XPS. And by looking at the copper 2P and just making a very simple empirical reference to reference data, we can make a conclusion about the chemistry, the chemical state of the copper nanoparticles. So in this case, because we don't see this sort of very distinctive shake-up structure, we very quickly identified the chemistry as copper 1. Obviously, there are sort of numerous assumptions that the nanoparticles are spherical, they're identical in size, and that very often is not the case. But XPS can still allow you to maybe identify contamination. So have you got contamination of the nanoparticles? Have you washed them? Has the synthesis been successful? Have you functionalized? Maybe if you're beginning to look at a sort of core shell nanoparticle, where we can use XPS in this sort of idealized model to look at the shell thickness. So XPS can, in fact, give you information on nanoparticles, and the models are being extended to sort of these non-idealized samples as well. So I think, yes, XPS is very much at the sort of limits of its capabilities in terms of nanoparticle characterization, but there is still definitely a sort of role for the technique for these type of samples. So how does SEM cope with SEM EDX cope with nanoparticles, Matt?
Yeah, I think of course there are both good and bad examples. I think I recently had a look at some rather small 10 nanometer gold nanoparticles with a thin 2 nanometer rhodium coating. This sample is provided by University of Oslo Department of Chemistry, and it was just interesting because I think here we also can see that we are pushing the SEM envelope. Top left image here shows you an SEM image in transmission mode, in bright field STEM mode, at 1 million times magnification. So really high mag in the SEM. We can see the 10 nanometer particles. We can see some crystallographic contrast, some channeling contrast. So we can get a feel for that they are not amorphous, at least. We cannot really see the rhodium layer. So that's hard in those images here. Then we tried with EDS to analyze these. And we can see that with a traditional EDS detector that looks from the side and collects a rather limited solid angle, that 2 nanometer rhodium coating is not enough material to give us any useful signal. Then we tried with a detector that has a large solid angle, so placed on an annular detector on top of the sample, give us maybe 50 times more solid angle than with the other detector. Then we start to see the rhodium peak. So then really that small trace amount. So then we try to do some mapping just in a few minutes to see that if, can we see a distribution of rhodium here? Well, I guess that maybe you have to be a little bit optimistic, maybe interpreting that data, but maybe with some longer measurement time or some more optimized measurements, maybe we can push the envelope to do that. I think this is in a way, this would be more of a TM, a high resolution TM challenge rather maybe than the SEM. So there, of course, even for, as we said, the techniques that we love, right, Adam? Both XPS and SEM EDS. I mean, it's kind of borderline what we could do here, but of course we still get some useful data.
That's right. I think, and that does bring it back sort of almost full circle, doesn't it, to the jigsaw of analytical techniques that are available to us. And I hope as we've gone through this webinar that we have sort of highlighted the capabilities of both techniques and where they can be complementary and add to a greater picture of your material. So there are the conclusions. I think it's, I hope it's been a useful exercise. It looked like it was almost a sort of 50-50 split between XPS users and SEM users. So I hope that we've highlighted the strengths of the respective techniques.
So maybe it's a good time also for adding some Q&A things that we have. So we actually really good timing, because the sample owner from this Oslo sample, so Wallace from the Department of Chemistry, is online. This is great. Thanks, Wallace, for joining in. And he said, "It's my sample." Yeah, and actually it just has about 1 atomic layer of rhodium. So my estimate of 2 nanometers were, far above. So we're almost seeing a single atomic layer of rhodium on those nanoparticles. Really cool, I think. Thanks for pitching in with that. I commented also about the complementary techniques of glow discharge, as I mentioned before. And of course, it is always hard in these overviews, when you look at the different techniques to cover all the aspects. Of course, that is true. So absolutely acknowledge that can be a useful technique. Also,
There's an
I added.
Oh,
Yeah,
sorry, Matt, talking over
no,
you.
it's just I added and actually a question in the beginning, just to have as a backup question about the using EDS for thin film measurements. And there was also one of the comments here that you could use EDS or EPMA, that participant said, what of course is electron probe microanalysis. So SEM EDS, but in a more, what should we say, a more dedicated format. So of course you can vary the acceleration voltage and then look at the different penetration depths, and then make a model to calculate film thickness with EDS as well. I think that brings out also the conclusion about surface sensitivity. I think that the XPS actually really shines in that range, 1 to 10 nanometer range of surface, where the SEM EDS maybe 10 nanometers typically, and thicker, up to maybe a micron, is kind of its comfort zone. And then if you need to go to higher, thicker materials, I think again, glow discharge, absolutely a technique. Maybe that is similar in surface sensitivity to the SEM EDS model, or even XRF, where we take X-rays going in and X-rays going out. That gives us the ability of looking at, I don't know, at least 50 microns or something like that in thickness. It struggles when we go below 10 nanometers for sure, but for thicker layers, of course. And it depends on what you're looking for.
Exactly. I think that's where I always sort of start getting excited about the surface. A lot of things like adhesion or catalysis, that's where the action happens. It's really that very sort of surface adsorbate level that you want to characterize from a sort of application of the material for a particular purpose. Sort of thinking of biofilms, biofouling. If you can prevent those biological materials from kind of getting a foothold on that very outer surface, then you stop their proliferation. So that's again that sort of where the real outermost layer of your material is dictating its application. I did notice while we're still sort of talking of depth information, one of the comments was, doesn't depth of XPS depend on the X-ray energy? Yes, it does. Can't you just increase the X-ray energy instead of using EDS? The difficulty, obviously, for XPS is that the way we generate the X-rays in the lab, we use an anode with a particular coating, and that gives us X-rays of a sort of characteristic wavelength or energy. And because we then monochromate, we're kind of very limited to the combinations or the X-rays that we can use in a lab environment. So there are a number of sort of commercially available sources: aluminium, magnesium, zirconium has been used in the past, chromium, gallium. So if you want a sort of continuously variable, you're then going to sort of look at using a synchrotron source, which is kind of beyond the remit of where we are.
You see that the question there about the quantification, Adam? I thought that would be something for you to answer. The response factor.
I'm struggling.
So, yeah.
To find the question. So yeah, essentially, we to sort of imagine what the question is. We do have to use what we call a relative sensitivity factor, and you can think of that as essentially the probability of creating that photoelectron. So each sort of core level will have a relative sensitivity factor, which is relative to typically carbon, sometimes fluorine, and then we say the probability of creating an aluminium 2p photoelectron relative to the platinum is a half. So there are a set of sort of calculated relative sensitivity factors, which are determined by the sort of physics of the photoemission process. There is also the second correction that you must do for the transmission function of the spectrometer. So that's the probability of getting that photoelectron once it's been created from the surface to the detector. So the transmission of the spectrometer. So there are a couple of corrections required.
But I think still, in general, I think XPS is seen as a reasonably, what should we say, simple method for quantification, right? It's well suited for quantification.
Yeah, that's right. That's sort of the take-home message I would definitely.
Yeah, I think so. I mean, there's another question from a good friend of mine, Matt. He asked about particle sizes that he is often looking at. I mean, where the particles are hundreds to thousands of nanometers. And they're not really nanoparticles, or they're not really films, but they are somewhere in between, often too small for XPS imaging, right? And the composition varies depending on morphology and varying electrical conductivity to the stage or the sample holder. There are challenges for SEM EDS due to shadowing, and we talked about the detector sitting on the side also in the SEM case. So how would be a useful workflow for analyzing those kind of particles? Yes, I think in a way, of course, XPS for a particle which is a micron big, it's too small to be imaged by XPS, but it still will react like a bulk material when it comes to the analysis, I presume.
Yes, and I mean that's the challenge then is because a lot of the assumptions, and again, sort of relating to the relative sensitivity factor and the transmission function, a lot of that quantitative nature of XPS is assumed that the film is sort of, or the sample is uniform laterally. So then
are you very sensitive to topography? I mean, we had the shadowing thing, yes, of course, because you're illuminating with X-rays from the side, so of course you are sensitive to shadowing.
Yeah, that's right. But also, that topography and the sort of angle of emission from the surface can start to sort of cause challenges as well. So yeah.
I think on the SEM side, I think one thing that we've seen with this, I talked about that detector with a larger solid angle. Of course, that is an annular, and that detector would actually collect a symmetric EDS map, or which would have very limited amount of shadowing. So again, either going for that kind of EDS detector would help, or also we have in some configurations we have more than one EDS detector. So we have one from each side, one from the other, and sort of then topography is more or less cancelled out in that measurement. So that's another way of approaching that, I think. No, but good.
Right. I'm very conscious of the time, Matt.
Of time, yes. Well, you know, we get carried away. It's interesting stuff.
Yeah,
So,
yeah.
and I think most of the attendees are still with us. So I really appreciate that you taking your time for joining us today in this webinar. And again, Adam, thanks for doing this with me. I think I really enjoy this. To the audience, again, it is recorded, and we will share the recording. Give us a couple of days to fix it up. And again, please get back to us with the comments, further discussions, or questions. We really enjoy the conversation.
Great.
So, and with that, I think we just close the webinar for today.
All right. Thanks.
All right.
Bye.
Thanks. Take care, everyone.